So this experiment that you'll do today, Lab C1, really looks at how resolving vectors into its components can be useful to you. You'll have the marble launcher itself set up with a photogate this time attached, and the photogate will measure the speed of the marble as it comes out of the marble launcher. That speed of the marble when it comes out is actually this thing right here that shows a V with an arrow across the top. That's showing that it's a vector, and you'll know that number because you'll know the distance, actually not the distance, but the diameter of the marble, and you'll know the time that it passes through the photogate. So that will be a known quantity to you. The angle that you see there, the angle theta, will be the angle of the marble launcher, and you'll know that quantity as well. Right thing. So here's the next page. Yes, I want you to go through and answer some of these questions, but I want to talk about this picture right here, because again, this is the picture, the marble launcher. This page, we want to really focus in on that triangle. So I already said to you that you're going to know this number up here, this V with the arrow across the top. That's equal to the speed, or actually velocity in this case, because it does have a direction, but it's the velocity of the marble coming out of the marble launcher. And you'll know the angle theta, which is the launch angle. So if you remember your relationships, you've got SOH, CA, TOA for your trig relationships, and we can use those to write some expressions for this triangle that's over here. So we can say that sine theta is equal to the opposite, which is this one over here, the initial vertical velocity, divided by the hypotenuse, which is V arrow. So V yi, yi divided by V arrow. That's a way of expressing sine theta in terms of the opposite and the hypotenuse over things that we know and don't know. So the initial vertical velocity is actually something that we want to know, and that would be equal to V arrow sine theta. So all I did was rearrange the equation, but we're going to use this one in just a few minutes. Now I'm going to switch colors, and I'm going to look at how I can express the other horizontal component, which is Vxi. So Vxi will be cosine theta. That's probably the best relationship to use, where it uses adjacent, which is Vxi, divided by hypotenuse, which is V arrow. So if I rearrange this equation, I can say Vxi equals V arrow cosine theta. So again, I go back to the fact that we'll know theta and we'll know V arrow as well for both of these, so we could figure out those initial components if we wanted to. A bit further below here, we see some expressions, and what they're trying to do is write equations that represent the horizontal velocity, which is Vx, the vertical velocity, which is Vy, the range, which is x, and the maximum height, which is y. Now these expressions right here are written as generic terms, and in the next question on the next page, it's asking you to start simplifying them. And I'm going to use this page right here, and I'm going to show some of my work and then recopy it onto the next page. But I want you to realize that there is no horizontal acceleration. So this V, oops, wrong thing. Let's try that again. This, okay. This part right here, AX, is actually equal to 0. So this entire term right there will be equal to 0. So Vx is going to equal Vxi. So the horizontal velocity is equal to the initial horizontal velocity that came from the marble launcher. It doesn't change. That is the inertia of the object. So the next equation you see here is Vy. So this is the vertical velocity. And you have that initial vertical velocity. And then we also know that the acceleration acting on anything in the vertical direction is equal to gravity here, at least on Earth. And so that AY term right there is gravity. So the first thing I'm going to do is rewrite this as Vy equals VYI plus, oops, not plus, try this again. It's actually the point I want to make is that it's minus G times T, because gravity is acting in a downward direction. And so gravity, when it's going down, is negative. So there is a negative sign right there. Now, we actually know from the first thing that we did up above that VYI, this thing right there, we know what that is, so we can substitute this in. So this gets a little bit messy. I'll change colors. I'll write it in black. VY equals V arrow sine theta minus GT. So this equation that I have up here, Vx equals Vxi, that's a big one. And then this Vy equals V arrow sine theta minus GT is another important one. So now let's look at that range equation. So we know that the range equation, the initial horizontal distance is equal to 0. So that first position that we're starting at is 0. So that quantity right there, let me switch colors again. That quantity right there, this one, oops, try that again. This quantity right here is equal to 0. So then we have the initial horizontal velocity times time, and then we have this acceleration term, but there is no acceleration in the horizontal direction, so this quantity right here is also 0. So that allows us to simplify and say that x equals Vxi times t. And we can substitute into that one even further and say that it's V arrow times t times times cosine theta. Oops. So right there is our range equation. And the last one that we have to work with is that of maximum height. So we have y, that's what we're trying to solve for. And we know that the initial position is 0, but there is a vertical acceleration, and that's gravity. So this term right over here is going to become 1/2 gt squared, but it'll be negative. So then we'll have y equals Vyi times t minus 1/2 gt squared. Now looking at this, we can plug in here for that initial horizontal velocity, the Vyi from up above. So that is y equals V arrow times t sine theta minus 1/2 gt squared. Probably should have written that in black. That's our third equation that we want. So we're going to move over to the next page and we're going to rewrite them. For this next part, we want to look at the equations we have and recognize that the maximum height at that point, the velocity is equal to 0. So we're going to take Vy equals V arrow sine theta minus gt. And then we're going to say that this part right here is equal to 0. So we can rearrange this equation and we have gt equals V arrow sine theta. And again, as much as it seems like something different, we know everything here except time. So time will equal V arrow sine theta divided by g. Now in this last part, we're recognizing that gravity acts only in the vertical direction, not in the horizontal direction. So x equals Vx times t. And we know that that is also V arrow times t times cosine theta. So if we want to rewrite this in terms of what we know above, then we could say that we can substitute in for time. we have x is equal to v arrow times v arrow sine theta over g times cosine theta. And so that equals 2v arrow sine theta cosine theta divided by g. Now, those of you that know trig, and actually know trig identities, know you can make a substitution in there for sine theta and cosine theta, but you don't have to do that. Those of you that don't know what I'm talking about, don't worry about it. Okay, on this page is showing you how to set up the PhotoGate and kind of set everything up. It's very similar to yesterday's experiment where you have the tape measures or the meter sticks on the ground to try and mark your range. Now here, unfortunately, my note that is up here in the corner is hard to read, but what that's trying to tell you is that you need to use 4 different spring settings. So you need to do launches at notch 1, notch 2, notch 3, and notch 4. And then you need to do 6 angles at those notches. So for example, you can set it at 1, spring scale 1, and then do launch 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, and 70 degrees. That would give you 6 pieces of data. Then you would do that same thing, exactly the same angles, for spring scale setting number 2. And then you do it again for spring scale setting number 3, and so on. This page, here you're going to move your data over, and you'll have your launch angles across the top. So for example, if you use the ones I talked about, 20, 30, 40, 50, 60, and 70, then you can figure out the initial velocity, which is the diameter of the marble divided by the PhotoGate time. That goes right in here. And the bottom row is your measured range. So right here, this is all data. It gets transferred from the previous page. The top row is your predicted range using that equation that we just figured out, the one that said x equals 2v arrow sine theta cosine theta over g. Using that equation, you predict the values that go right up in these spots right here. Okay? And you should be fairly close to your measured range. It's not perfect, but it should be close. Once you get this table figured out, you're going to need to graph, and I would highly suggest that you take the time to graph on the graph paper on the next page using different colors to show the different sets of data. You'll notice this message did come through. I said use different colors for each spring scale setting. You're going to use a solid line for the theoretical values and a dotted line or dashes for your measured points. It's really a great graph to get what's going on if you do it by hand, or at least estimate it by hand, and you can do that right on your iPad. So your goal is to finish this lab in class and then to have it ready for questions on Friday.